Carlton, you want to start us off with the number 1 here? Just reading it out loud. I know you have a nice big voice.
Common refrain for teaching mathematics is, when are we ever going to have the answer is now?
Now, right now. So number 2, Bridget?
Let's look at the following bar graph showing the average cost of tuition fees.
All right. So anytime you submit a graph to me, or really to anybody, the graph should always have a title so that you know what's going on in the graph from looking at the title. Your axes should be labeled, and you should have a scale. Okay. So you all spent a few minutes analyzing this bar graph, and you have some great observations here. In fact, we came up with several that were not mentioned in my first class. So let's take a look. I think everyone's talking about the fact that the graph is rising or increasing as each year goes by. Some people have said it's growing and tuition and fees are getting more expensive. Okay. Someone says the graph is relatively linear. And I like the fact that they said relatively, and we'll talk about that in a second. Cost of tuition and fees increases every year. So I'm going to write a couple of these down for those people who want to come back and look at the annotated notes in Moodle. So we have, let's see, and you want to be specific. It's the cost of tuition and fees. I know you were just writing up, but if you were responding to this question on your project on the back table, you would want to be more specific, like the cost of tuition and fees where? At public, because it's going to be very different for private. So you didn't have to write this on the boards, but at public 4-year colleges, increases every year. That's definitely what some people noticed. The fact that people said it was relatively linear, why didn't they say it was linear? Why couldn't you make the statement that it's linear? Yep, Ben?
Well, linear suggests that it goes at an increased rate. So like.
Well, this is an increased rate.
Well, I mean like constant.
Constant increasing rate, right? That's the key, right, Ben?
It's like, well, it kind of does that.
Right, exactly. So we can't say that from year to year the increase in tuition and fees is the same or constant. That's what makes a straight line a straight line, is the fact that as your horizontal variable increases by a unit, your y variable increases by exactly the same amount per unit increase. And you can look at that and say it's kind of linear. It looks it, all right? And so one of the things that you're going to be doing in your first project is you're going to be downloading a free software package called GeoGebra, which you can use in any of your classes forever and ever. So even when you transfer, it's a fantastic package. Notice I just plotted these 11 points. So certainly, depending on, and this is kind of the tricks of your eyes, and that's why it's kind of nice to have a way of finding an equation. We're going to be talking about this in a minute that can model this growth. But as you can see here, as I sort of change this scale or spread it out, that looks really like a straight line, doesn't it? Very close. But look what happens when I then take this scale and I do this to it. Or when I actually ask the computer to fit an equation to this, look what equation it fits to it. What kind of picture is that? It's a parabola, and what kind of equation would that be? Would it be a linear equation? Quadratic, yeah. So, and notice here's what they're saying it would look like: 4.39x squared plus 341x plus 3194 if we round, and that's what you're going to see on the next page. So you can see here that, you can't just look at the data and you can look at it and you can say, yeah, and maybe a line would be a good fit as well. Let's see what the line would look like. I'm just going to go down here and say fit, let's let's say Polly, and I'm going to say list 1, and I'm going to say first degree. And there's the line that fits that data the best. So again, you'd say, well, they're relatively close. Let me spread this out again, this axis here. And you're saying, yeah, hey, you know, the line goes through the data, the parabola goes through the data, but one of them, if I really like increase the distance here on the scale, you'll see one fits it just a little closer than the other. And this is where we're going to be spending some time in a few weeks, is talking about models and which ones fit better. But you see how they're really close, but one of them actually is a little closer to all the points than the other. Okay, so linear, yeah, linear is not a bad model for this or a bad representation of this data, but a quadratic one isn't a bad representation either. And there's actually a statistic that we calculate that tells us how good the fit is. Okay, and so we have sort of an objective way versus our eyes of actually telling which one is the better fit. All right, so that's a little bit more than what you need for today, but I just thought I'd show you where we're going at some point. Freshman year fees are almost $1,000 less than senior year. Where's freshman and senior year on that? I don't see freshman and senior year. What? Okay, but this would be, okay, so all right, this is the fee regardless of whether you're a freshman or a senior, right? This is the yearly fee. So you were just comparing the first 4 years there, Eli? Is that what you were thinking? Any 4-year gap, okay, is about $1,000 difference. Is that what you're thinking? Okay, well, let's look here. 2004 to 8, is that a 4-year $1,000 gap here? 1, 2, 3, 4. Okay, about 1,000, and yeah, okay, so that was, I see, so you're looking at every 4 years. Okay, tuition almost doubled in 10 years. That's a really interesting statement, that tuition and fees almost doubled in 2 years. No seats for you? Okay. That's because we have someone on the wait list. Back on. Okay. So that's an interesting statement, that tuition and fees almost doubled in 10 years. And at the very end of this course, we're going to be looking at logarithmic and exponential functions. And there's a little rule of thumb where you try to figure out how long it takes for something to double and what the rate would have to be. And so if you say 70, this is a constant. This is an approximation. It's a rule of thumb. And this thing doubled in 10 years. If you do that, that tells you the approximate rate of increase, the average rate of increase of tuition and fees, 7% a year. That's a huge jump every single year. Huge percentage increase, because each year your base gets bigger and bigger, and you're still taking that same percentage of a bigger number, so your increase is going to be bigger and bigger. So that's pretty incredible, 7%. So that was a really neat thing to notice. Let's see. Quadratic, someone said it was quadratic and not linear, so that's interesting. There's a break in the graph. That's what this little thing right here means. Whenever your scale for your axis starts other than 0, you have to put that little break in there. It's just a little squiggle. And let's see, what kind of questions would you like to ask? Where does all the extra money go, and what does it benefit? Well, where does all the extra money go? I can't answer that for 4-year institutions. I can talk about 2-year institutions, and there's not a lot of extra money to go around. And part of this is, oh, let me just put that one down, mention that one. What will my children's tuition and fees cost in the future? Because that's kind of what we're going to be looking at today. Let me write both of those down. What will my children's Who wrote that? I'm just curious as to how long that will be. Christina, how many years will that be, you think? 5 years? Okay.
Well, he's 5 now.
Oh, he's 5. Okay, so your child's 5. So if your child, let's say another 13 years or so, 13 to 14 years, we can take a look at that today. If things continue, and if this model is accurate, and it's continuing to grow at, approximately this rate, whether the quadratic model would be a good model for 15 years from now or 13 years from now, we don't really know. Okay, and then the other thing is, where does all the extra money go? Where does all the, no, that's a different song. The extra money go? And who does it benefit? Yeah. Well, why such a steep rate? How will this affect students in the near future? Yes, of course you're concerned about that. How does it affect AFFECT, your near future educational costs, right? Absolutely. These are all the types of questions that mathematics can help you get an answer to, okay? And in order to answer these questions, we have to create, turn your page, a mathematical model, okay? So let's see, who wants to read this for us? Any volunteers? It's not that hard. Okay, Joshua.
The good news is that it may be possible to answer.
I really like that. You said it with like feeling. Go ahead, do it again so they can hear.
That it may be possible to answer using mathematics. We can work with real.
Recorded. So as you can see, both visually, the graph gives you a nice visual representation of this symbolism here, which we call algebra or an equation. So sometimes it's really helpful to have both for you, so you can see the relationship between the algebra, which is a symbolic representation, and a visual. Some people like having tables as well. That would be numerical. Okay. So let's take a look here at the first question. Use the formula. We could also use this word, use the model, if we wanted to find the average cost of tuition and fees at U.S. public colleges for the college year ending in 2010. So you want to help me start this? How would I start this? How would I find the average cost of tuition and fees? Plug in 10 for X because X represents years after 2000 or since. So the first thing I do is I say, okay, I go to my definition of X and I say X is equal to 2010 take away 2000, which is 10. And I know I have to find the value for T when X is 10. That's my job. And this little graph, this little formula or model here is going to help me do that. So all I have to do is go into my equation, and where I see an X, I substitute a 10. And again, I rounded this off so that it makes the calculations a lot easier. So this equals 400 plus 3,410 plus 3,194. And so off on the side, I don't have my calculator. I do, but okay. I just wanted to use my brain for a little bit. 489. Oh, what is it? Is that right? Did I do that right? Doesn't look right. Oh, so it's this way. Okay. So I added wrong. Okay. 7,004. So that 7,004, is that the actual amount of tuition and fees in 2010? What do you mean? It isn't? Or is it the actual average tuition and fees in 2010? It's an estimate. It's an estimate. What is the actual average tuition and fees in 2010? $16 higher. And where did you get that information? Right here. Here it is. This is the actual data point. This point is from your graph 2010, 720, or using our definition of X, 10, 720. That's the actual real life value. This is the actual data. Okay. What we got from our model predicts or estimates that our answer is 10,7006. This is an estimate. So it would be slightly below there. According to my model, my bar wouldn't be quite as high. It's probably even closer than what I've drawn, okay? My bar wouldn't be quite as high. So my model estimates the average cost in tuition to be 4, right? Sorry about that. 7,004 when the actual value is 7,020. What do you think about that as an estimate? Pretty close. It's pretty cool. Yeah. So a pretty good model. In fact, it only underestimates the actual cost by $16. Okay. Okay, so I would like tables 1, 2, and half of 3, which means you get cut in half, find the average tuition and fees for the college year ending in 2014, and then the rest of you to do 1990. And when you're done, put up your flag. When your table has the answer, put up your flag, and then confer with the other table. And when you're all in agreement, put the answer on the board, okay? So the first question about the college year ending in 2014. Since 2014 goes into the future from our data set, right? We call this extrapolation. This is a prediction. You're making a prediction. So you are predicting the average cost of tuition and fees. All right? And this is called extrapolation because it's outside of the data set, outside the range of your data. Okay. So again, we have to be fairly cautious whenever we go outside our data set because our model is built on those values from 2000 to 2010 only. That's the only data that came up with this equation here. So whenever you're asking questions that go into the future or the past, you have to be a bit skeptical and cautious. So 8,752, that would be last year's tuition and fee rate. Does that seem plausible and reasonable to you, given where the costs are today? Okay, seems okay. Now, for 1990, since our data starts with years since 2000, what would be the answer for X here? -10, right? Because you start with the year you're asking about and you subtract 2000 from it, and that's -10. It's 10 years in the past. You think 10 years prior to 2000, the average cost of tuition and fees at four-year schools was $184? Yeah, me too. Okay. So that's not plausible at all. And if you look at this graph, we can see the direction that things are going in once this graph gets just beyond, like somewhere between 1990 and 1988, it's actually going to go down into the negative. So this model that we're using to predict these 11 points here breaks down. That's the language you use. It's not a good model outside of this data set, particularly in the past. So far, a few years into the future, it seems reasonable. So the actual language, whenever you get a result from using a model that goes outside of your data set that doesn't seem plausible or makes sense or isn't reasonable, you say that you have model breakdown. This is something you want to highlight in your notes, particularly for your project. You may want to use this term at some point. Okay. So I've given you a note here about the average cost of tuition fees, room and board for private schools, and that was up 14% over 5 years. Okay. And the average price tag for 4 years schools, public, was a 20% jump. So these are becoming just increasingly more difficult for people to get an education and then not have without enormous debt afterwards, which is changing decisions some people have to make in their life. So this is a huge concern, and it's politically a huge concern, but we won't go there right now. All right. Sets. Let's talk about sets. No, not what you think I said. SETS, sets, okay? Who wants to read this one for us? Eli? Come on, Eli. Got to get a smile out of you somehow, right? Okay, I think you're all familiar with the word set. The objects in a set are called the elements of a set. We may write a set by listing its elements between these little curly braces. So whenever you see these little curly braces, that indicates a set. It's just like saying the word the set of. Okay, so when you can list each element in a set, we call it the roster method. Just like I have class roster. It says right here, class roster for Math 107B. There's the set of students in this classroom right there on my roster. Okay. So if I wanted to list, let capital A stand for the set of Three Stooges, and I would notate that by using a capital A with an equal sign. I have to always put my set, my elements in a set between these curly braces, and then I list each element, Larry, Mo, and Curly. Although a student corrected me last semester and said you forgot Shem. So I guess Shem came before who? Curly? Or was it Larry? I don't know. But anyway, those are the three that I remember when I was growing up back in the dark ages. Okay. So what I want you to do at your seats right now is let B represent the set of the 4 Beatles that actually arrived at the JFK airport in 1964. And to help you, I gave a little picture here in your lecture notes. So see if your table can come up with the names of those 4 Beatles in 1964. What do I write after the equal sign here? Oh yeah, I got to start with those curly braces or I'm in trouble because it doesn't represent a set, right? So who thinks they have all 4? Full names. Ooh, okay. He said he was a Beatle nerd, is that right? Joseph, so what do you have, Joseph? John Lennon, Paul McCartney, Ringo Starr, and George Harrison. All right, good. I actually remember, I'm dating myself, I know, but I remember sitting in a living room with a black and white TV and watching all of these young teenage girls screaming and crying in the audience when they were playing on the Ed Sullivan Show. And I couldn't understand. I think I was like 8 or something. I don't know. How old was I? Yeah, I was 8. And I was like, why are they crying? I don't understand. Anyway, I understand now. So I used to have all of the previous years, I used to have the 7 Dwarfs, and that caused big problems. So I went back to the Beatles. So if you think the 7 Dwarfs would be more fun, send me an email. All right. Now, this next section here, 8 in your notes, is a pretty critical section because we have 3 ways to describe sets in this class. There's actually 3 different notations that we're going to be using throughout the class. One of the notations is this first one called set builder notation. And in general, let's just start with the example I gave you right here. Notice it starts with the curly braces and it has an X and then this straight line and then it has an inequality. So a set builder notation will always start with these curly braces. You'll have your variable. And sometimes over on the right here, you have to say what number set your variable belongs to. We're just going to assume for this class that X is always a real number. So we don't have to write the following. Often you'll see this, like if you're reading another textbook, you might see this. X belongs to the real number set, and then you'll see X greater than 2. So this is the part we're not going to bother putting in. We'll just assume, okay? We'll just make an assumption here that X is a real number. And then the statement that comes after this vertical line is something you can test. In this case, it's an inequality. So if I say to you, is 0 part of this set? You can test it. You say, well, is 0 greater than 2? Nope. 0's not included in this set. Is pi included in this set? Yeah, pi is bigger than 2. So pi's a real number in this set. Okay? Don't just think integers or whole numbers like 2, 3, 4, 5. It's an infinite number set. So this represents the set of all numbers greater than 2. Strictly greater than 2. No? Right? So here we're just on to the right of 2, okay? So that's one way, that's step builder notation. A more visual way of representing this set is to use a real number line, and you can actually shade it in with a different color or a different, line width. And you put a parenthesis at 2 because 2 is not included. You put a parenthesis on the line, and then you shade all the way to the right. Well, you can't go all the way to the right because it goes on forever and ever. You just put an arrow to indicate this continues to the right forever and ever towards positive infinity. Now, the notation you're going to be using often in your MyMathLab homework, at least right now, is interval notation. And notice I have this little arrow that goes from the parenthesis at the beginning of this notation up to the number line. Because when your endpoint, this tells 2 is an endpoint. 2 is one of your endpoints. It's your left-hand endpoint in this interval. And when it's not part of your set, when 2 is not an element in this set, because x has to be, all the numbers in this set have to be strictly greater than 2, you use a parenthesis. And then you say, well, where's my right-hand endpoint in this set? Well, there isn't a specific number because it goes on and on towards this thing called positive infinity. So you use the infinite symbol, and then you use a parenthesis. So why would we use parentheses here with infinity? Why don't I use, well, if you read this, it says you use a bracket. See this bracket? When you want to include something, you use that bracket, either on either end. That includes that endpoint. So why wouldn't I use a bracket for infinity? There's no endpoint, right? There's no number called infinity. It's a conceptual idea. All right. And I often will call the bracket, when you include something, the staple. Doesn't that look like a staple? And when you staple something together, you're including it. So I often think about that number being stapled right on the number line. So in other words, if this said x was greater than or equal to 2, then this is what it would look like. It would look like 2, and then it would be like that. And then your interval would look like this. Open circle and close, yes. Some of you might remember open circle for when you don't include close, and that's what I used to use. But when we changed the book, this is what your book uses. And what's nice is it goes directly with the notation of your interval notation. The same symbol used on your real number line actually corresponds to the parenthesis or bracket in your interval notation. Okay, so let's quickly finish off number 9 together. Here's a set right here, set of real numbers. Let's do both interval and set builder notation, and we'll see how we do. So anybody want to take on the challenge of representing that set? And we'll do a description in words as well. Let's see how we do here. Either one of those. Anybody want to take that on, that set? Either a word description, set builder, or interval. Two, 4, 2, okay. -1, -1, 4 with square brackets and a comma. How about, does that look good? Okay, because we're including -1 and we're including 4. Notice that he automatically said -1 goes first and 4 goes second, because -1 is your left-hand endpoint, therefore it's the first number. It's always the smallest. And 4 is your right-hand endpoint. It's greater than -1, so it goes second. Okay. How about set builder notation? Curly braces x such that, and how would I write that set of numbers using set builder notation? Finally, a word description, the set of all real numbers between x and 4, between 1 and 4, inclusive, right? We're including both the 1 and 4. -1, thank you. Okay, how about interval notation for the second set of numbers represented here? Let's call this number 2. Yep, Bridget? Perfect. Any questions on that? Okay, you now have 20 minutes to